Hello everyone and welcome to today's webinar looking at application of machine learning for actuaries, brought to you by the Actuary and kindly sponsored by RemitRix. I'm Francisco Sebastian, editor of the Actuary, and I'll be chairing today's webinar. Before we get started on the main event, we have a few housekeeping points that I would like to clarify to you. First, we will hear a presentation from our guests from RemitRix, and this will be followed by a Q&A. So as you think of questions during the presentation, please type them through in the comment box below, the blue box below the slides on your screen. We will then use as many of these as we can in the Q&A. The webinar is expected to last about 1 hour and it will be recorded. If you have any technical issues during the webinar, please click on the technical help box, which is the red box below the slides. At the end of the webinar, you will be able to send us your comments and recommendations for future webinars. So please remember to complete this short exit survey when you leave the webinar. We will also make a recording and copy of the slides available afterwards, and this will be emailed to you in due course. So now, after these brief points, I would like to introduce our speakers for today. First, I will introduce Effie Moore, who is the CEO of RemitRix. He has 10 years of experience in financial risk management in the largest life insurer in Israel, and he's very hands-on in developing solvency applications and various automated financial tools, back and front end. We also have David Engelmeyer, who is the Chief Actuary. He has over 20 years of experience in actuarial work and consulting in all areas of insurance, including life, health, pensions, P&C, as well as all disciplines of actuarial work, including pricing, valuation, illustration, risk management, and data structuring. And finally, we also have Neta Shashar, who's a machine learning researcher, and she's a data scientist in a top-tier startup focused mostly on predictive modeling, including classification, regression, and survival supervised models. She has also done work on clustering and partitioning algorithms. Now, after the introductions, I would like to also briefly mention that, as you will hear from our speakers during this webinar, in recent years, machine learning-based algorithms have become very popular in almost every industry, providing more accurate solutions to various problems. Some examples of these are customers' churn predictions, user segmentation, or risk assessments. So this is basically what we're going to cover today, and now I will turn it to Effie Moore, who will kick things off. Thank you.
Thank you, Francisco, for the introduction, and thank you all for joining us today for this exciting session. Still, we have gathered here today with more than 1,700 actuaries listening. So today we will be demonstrating the power of machine learning as a solution to manage risk under Solvency II. Of course, there are many other benefits you can extract from using machine learning in the actual field, be it on the business side or other modeling tools. However, the major gaps that we intend to solve with our set of simulations are the limited usage of big data in the insurance space. It is also the separation of risk management tools from solvency, which also reflected in the way risk managers and actuaries work, for example, given managing assets and liabilities separately. The purpose of machine learning is to improve the accuracy of the prediction by, for example, improving segregations from current models that actuaries use. Its use may result in an increase of your solvency ratio as well. An additional significant side benefit of the incorporation of machine learning process is to automate the parameter estimation, which facilitates frequent updates and use of ongoing accumulating experience data. Also, there is a great benefit from managing both assets and liabilities under one platform with a very advanced user interface tools. As a general view, you can see here the system architecture, when on the left side, we show the data files type for different input types required for the processing of the ETL, the extract, transform, and load, and all the way through the calculation of the standard model, the internal models, and the different risk tools. Eventually, it all boils down to the reporting system. So next slide, you will be listening to Neta, our machine learning researcher, who will describe the machine learning solution offered under the standard model engine. Neta, please.
Thank you, Effie. So as Effie and Francisco said, my name is Neta, and I'm a machine learning researcher here in RemitRix, and I'm going to talk today a little bit about what is machine learning, why do we think that it should be used in the insurance world, and specifically how we used it in survival analysis, which was our first POC. So in survival model, and I'm just going to say real quickly that I do assume some background in statistics and probability throughout this talk, but I do not assume any prior knowledge in machine learning. So if you don't have any background, that's totally fine. If you do have some machine learning background, then my apologies in advance. The first few slides may look somewhat trivial. Okay, so as I said, we decided to start with survival models and specifically trying to model and better predict lapse risks. And as you all probably know, in lapse risks, our goal is to estimate time to event being the lapse, for new customers based on our past customers and on our current customers. And traditionally, this is done in one of two methods. You either have a lot of domain knowledge, expert knowledge, and you start exploring and researching different behavioral groups, things that you know that groups that you know traditionally are different from each other. And then you estimate the survival curve of each such group in an aparametric manner. Or you use semi-parametric modeling like in Cox models, where you have a target variable, which is the time to event, and you have all kinds of covariates, explanatory variables, and you're trying to predict the time to event based on the covariates. And specifically for Cox model, that requires you to assume both proportional hazard and the linear relationship between the target and the explanatory variables, so it's somewhat limiting. And what we offer to do is instead to use machine learning algorithms to identify the different behavioral groups, the different groups whose survival curves are different from each other, and then to automatically estimate the survival curve of each such group. So first we must ask ourselves, what is machine learning? So this is one definition which I found in TechEmerge. I have to say I'm not a huge fan of it, but let's just go over it real quickly. So machine learning is the science of getting computers to learn and act like humans do and improve their learning over time in an autonomous fashion by feeding them data and information in the form of observations and real-world interactions. And so what I don't like about this definition is saying that the machines act like humans or that they learn in an autonomous fashion. That's really not the case. The machine can learn complex patterns and it can learn interactions as long as we as machine learners or as domain experts know what to feed to the machine. We have to feed the machine data. We have to make sure that the data is clean and it's not biased and it's representative of the real world. We as researchers have to define what is the objective, what is the goal for the algorithm, and then it can detect the patterns, but it doesn't do anything on its own. In practice, machine learning actually emerged way back in the 60s from pattern recognition. So really it's an old field, but in the last decade or so, it really gained new momentum. And the reason for this new momentum is the huge progress we made in computational power. So nowadays, most companies and even individuals have access to really strong machines. A lot of people are using Amazon's machines. So we have very strong computers. We also have storage, which is much cheaper than it used to be. So all companies hold on to their data about the customers, about the past customers. We have big data. We have big machines. And this is really the conditions in which machine learning algorithms can thrive. And indeed, if we look around us, we will see that it's heavily used more or less everywhere. So your recommendation system, when Netflix says you're going to love this movie or that movie, this is definitely machine learning. Fraud detection for PayPal, if they want to identify if a seller or a buyer is fraudulent, they will use machine learning. Sentiment analysis, like is done in Twitter a lot of the times before the election, they often use it. It's machine learning. Virtual personal assistants, obviously AI, machine learning, NLP, all of those are used behind the scenes. Face recognition, I don't think I need to say much more. Spam filters for Google, obviously personalized marketing. And even in the insurance world today, we have Lemonade, who raised a little over $120 million, I think. And they also promised to use machine learning techniques in their product. So it's really everywhere. And then, obviously, you have to ask yourself, why? So there are a couple of answers to that, if you ask me. First of all, as I said, it's ideal for big data. And a lot of the companies have big data because we've been saving our data and protecting it and keeping it for a couple of years now, and now we want to use it. And machine learning is really one way to use it. It's able to detect complex patterns, and by complex patterns, I'm definitely addressing things that are more complex than what a human being can detect, but also a lot of times more complex than what a classical statistical model would be able to detect, simply because for classical statistical models, if we think about linear regression or logistic regression, if we want first order or second order interactions, we have to say so. We have to manually insert them into the equation. Whereas for machine learning, we don't have to say anything. For most algorithms, we just let them explore the data, and if first order or second order interactions exist, the model will be able to pick up on that. So that's nice. The solutions are fast and flexible, and this is, I just want to take a brief moment to talk about that. It's not necessarily fast to train initially, and definitely not fast to validate or to make sure that it's working. It takes time, just like any other modeling process. But once you have the model and you're happy with it, then you can make small tweaks to it. You can add data to it. You can maybe transfer it to a slightly different domain without starting from scratch. So in this sense, it's definitely going to be much faster, and there is that flexibility in them. The process is automated, and because it's automated, it's obviously easily updated. So every once in a while, if I want to make sure that the model still generalizes well, I can check it. And if for some reason it doesn't, maybe because the data is not updated or something like that, I can easily update it. The next thing, and another very important thing, I think, is that you do get insights into the modeling process. And I think this is important because a lot of people that are talking about machine learning are referring to the algorithms as black boxes, saying that you don't really know what's going on there. You input the data and you get predictions and you have to trust them, and that's it. That's a black box. But that's really not the case. When you have a data scientist or a machine learner that knows his job, he does know what's going on in the algorithm. He does know how it works, and you do get all kinds of insights as to why the predictions were made the way that they were. So, for example, in GBM, which we will discuss later on, you could get insights as to which features, which explanatory variables were most important for the modeling, were most predictive. And this is, I think, very clear to everyone that can be very insightful and very useful for a researcher. And the last thing is that it's a growing field. And when I say growing, we saw just 2 slides ago how many of the big companies out there are using machine learning, and they're going to keep on using it, and they're spending a lot of their time, a lot of their money. They take all of the best academic researchers to work on all of those problems. And luckily, they do publish a lot of the results, a lot of the new algorithms and new tricks that they come up with. They either publish papers or in conferences. A lot of the things are open source, so we have access to the actual code. So not only are we able to say today that machine learning is often doing a better job than a classical statistical model, but also you can be pretty sure that in 2 years or 3 years or 5 years, you're going to have an even better algorithm or an even better implementation of a specific algorithm. And this, I think, is also very nice and very promising. Okay, cool. So let's assume that we all agree that we should use machine learning. I'm going to explain a little bit about decision trees, which is one of a family of models in machine learning, which is really one of the building blocks of machine learning. And I think this is the case mainly because they're very intuitive, they're very easy to understand. They often look like how a human being would think of things, so it's very nice. And apparently they're also quite powerful. So just as a reminder, we are trying to find different behavioral groups with different survival curves, and we have all kinds of covariates at hand. So it could be the gender, the occupation, the age, the city you live in, are you married, are you a smoker, whatever we have. And the very, very naive decision tree can look something like this when we try to divide our data according to gender. So we have females on the left hand and males on the right hand, and we try to estimate a survival curve to each of those groups. And in this case, this is just what a human being would do if he would try to research the data, right? But a human being may have say, okay, those curves look pretty much close to each other, so gender is probably not an important covariate. But a decision tree can dig a little bit deeper and can go ahead and look at females and divide them by their age. So females that are above 35 may act in a specific way, and females that are below 35 may act differently. And this is what we see in this case. So now we have 3 different behavioral groups, 3 different survival curves. And the decision tree can go on and build an even deeper tree and divide the males to those who work in construction and those who don't work in construction. And now we already have 4 different survival curves representing 4 different behavioral groups. And this, I think, is something that a human being would struggle because, as I said, it's very, very possible that a human being would just say at this point, at the first stage, okay, gender is not important. But also, if a human being has to split by age, he has to go over above 35, below 35, above 36, below 36, and so on and so on. And obviously, that will take a lot of time. And the same goes for industry, for occupation. So decision tree can do that for us very efficiently and very quickly. And so it seems like our problem is solved and decision tree models are what we should use. But the truth of the matter is that it's not that easy. The problem with decision tree models is that they are solving an NP-hard problem. And they're doing that by using a greedy search. What do I mean? They can't go over all covariates in all splits and check all of their splitting points, especially if we have continuous covariates, right? Because age is not just to check above 35 and below 35, above 36 and below 36. If it's a continuous variable, there's actually an infinite number of points we need to check if it's worth splitting on, and we obviously can't do that. So the algorithm works in a greedy manner, but this greediness makes it so that it may end up in a local optimum rather than a global optimum. And it turns out that there are a bunch of things that you can do within the framework of decision trees to improve on that and to try to make sure that you don't overfit or that you are more likely to get to a global optimum. But in practice, what we usually do and what is empirically more beneficial is actually to use a different family of models called ensemble models, where you build a lot of very simple base models, in this case, a lot of decision trees, small decision trees, not the very deep ones, but the small ones, which are very quick to compute, and then you combine them together. So what you do, as I said, you train the multiple models, you combine them in some manner. We're going to discuss how exactly to combine them, and you gain more power and more accuracy over time. So just so we're clear, so we're all on the same page, when we talk about machine learning algorithms, we usually divide them to unsupervised learning when you don't have labels, and supervised learning, which is what we're dealing with here, where you have labels. You do have past customers or current customers on which you know the truth, when did they lapse. And then under supervised learning, you could either use a single learner like one decision tree or just logistic regression, or you can use an ensemble of learners where, as I said, you take several learners and combine them together. And the way you combine them could either be by bagging, by stacking, or by boosting. We're going to focus today on boosting, and specifically on an algorithm called gradient boosting machines, or GBM for short, which is very powerful and very heavily used in a lot of different fields. So, gradient boosting machines, according to Wikipedia, so not a very scientific definition, but I hope a clear one, is a machine learning technique for regression and classification problem, which produces a prediction model in the form of an ensemble of weak prediction models, typically decision trees. So as I said, I'm going to assume that the weak learners are decision trees. We're not going to talk about other weak learners today. And I just want to say that it's not just for regression and classification problems. It can actually be adapted to be used in survival problems, as we'll see later on. Okay, so every GBM has to have three things. It has to have the loss function, because as I said, the machine does not learn anything on its own. We have to tell it what is the goal, and the loss function actually defines the goal for the computer. We have the base learners, also referred to as weak learners, because each of them on its own will not give us a lot of power, will not give us a lot of accuracy, but together we hope we do get the accuracy we want. And we have the additive model, which takes those base learners and combine them together. Okay, so loss function. That's the most important thing, presumably. What we want is to minimize the loss, obviously. So this is the objective. This is what we tell the machine that it has to try to do. And the function could be really any function in the world, as long as it's differentiable. But in practice, there are functions which are more heavily used, more commonly used. For example, if we're talking about regression problems, let's say we want to predict the wage of college graduates, we will probably use sum of squared errors. If we want to predict whether a customer is going to leave or not, that's a classification problem, and then we will probably use the 0-1 loss. But really, the choice of the function is up to the researcher, up to the machine learner. And it's according to the data, according to the goal, and again, just make sure that it's differentiable. So let's assume we have a loss function, and now we can go on to the weak learners, which are decision trees in our case, and I already explained a little bit about them. But I do want to take a minute and talk about the splitting criteria, because it is important. Again, going back to machine does not learn on its own, we have to say how to split. The algorithm can very quickly and very efficiently go over a lot of different splits in each node of the tree and decide which split is the best, but we have to tell him how do we define best. So one definition of best could be, please split the data such that the loss function will decrease the most. Or a different definition of best could be, please split the data such that the observations in the two nodes resulting from the split are as different from each other as possible. They are as heterogeneous to each other as possible. So again, choosing the split criteria is up to the researcher or the data scientist who is working the problem. And we also have some parameters that we need to tune when we use decision trees. Things like what is the maximum depth of the tree, or the maximum or minimum number of observation in each leaf. Leaf is a terminal node. Again, things that we do as part of the training and of the preparation of the model. And there aren't any distinct values on what should be the depth or what should be the number of observations for a leaf. It really depends on the data that you have, how much data, how different are the observations from each other, how many covariates, and so on. And so the last part is how do we combine the decision trees together. So in boosting, and specifically in gradient boosting machines, we have a sequential algorithm, which means we start with one decision tree, we'll call it T1, and we get predictions, Y1, and then we calculate the errors of those predictions. So E1s are Y minus Y1. Now we will build a second decision tree, T2, but we will try to predict E1. Why would we try to predict E1? Simple, because now we can update our prediction to be Y2 equals Y1 from our first decision tree plus the predicted of E1 from the second decision tree. And hopefully we will get closer to this total Y. And now we can do it again and train T3 to predict E2, and we will continue to do so again and again until we converge. So this is pretty simple. In practice, it works using gradients. It follows the gradient until what we hope will be a global optimum. And there's one more thing I want to talk about in this context. I said before, I briefly mentioned it, we need a lot of data for machine learning to work. So if we have n training examples, we want to use all n training examples for each of the trees that we're building. But we do not want our data set to be exactly the same, because then it's very likely that we will get the same decision tree over and over again. So what we do is that we add weights to the observations in themselves, giving high weights to observations on which we made big errors in the previous step. Okay, so the idea is if I made a big mistake on observation 3 in my first decision tree, I don't want to make another big mistake on it in the fourth decision tree. So I'm going to give observation 3 a high weight in this next iteration. And then another thing that we are doing actually is we add weights to the models themselves, because the further we do a lot of iterations, we sometimes build 500 or 1,000 trees. And the further you are down these iterations, the higher the chances that what you're modeling right now is actually just noise. So in order to decrease the risk, we simply give lower weights, called the learning rate actually, to the more advanced models. So this is how it would look like. Here we have the observations. The bigger observations, the bigger dots are the ones who has higher importance. We give this to a model, it builds some kinds of decision tree, and now, according to the errors of this model, we give weights to this set of observations. So now you see different dots are bigger than others, and we do it again and again, and eventually we have the final prediction. Okay, there are more improvements to this model, to this framework, just like in any other framework. So the reason we have the improvements is that the models may overfit. They are still greedy algorithms, so we still have some risks there. But it turns out that there are a lot of solutions that substantially reduce this risk. So we can add constraints to the loss function. We can add weights, as I said, to the models or to the observations. We can add some subsampling either to the observations or to the covariates, just to introduce some randomness so that we don't overfit on the training data. And again, this is just part of the work of the data scientist. Okay, so just so that we are all clear and that we are all on the same page, let's look at a toy example. Let's say that we have two covariates, x1 and x2, and we want to classify all of those data points to one of two groups, either orange or blue. Obviously, a linear separator would not do a good job in these settings. Correct me if I'm wrong. So let's see how one tree would do, and then we will see how a GBM would do. So we can start with one tree of depth 4. And it could look something like that, where you first look at x1, and if it's smaller than 5, then you're just going to say orange. And if it's bigger than 5, then you're going to look at x2, and then you would look at x1 again, and so on and so on. And we will get something like that, where the margins we classify as orange, and that's pretty decent. We do a pretty good job here. We have one miss, but that's not a big deal. And in the middle, as you can see, we have this part which is classified orange but has a lot of blues in it, and we have this whole section which is classified as blue but has a lot of orange to it. So obviously not a very good job. So we will go on to the next tree, and we will add it, and we will add errors just like we saw the algorithm does. And we will get something like this. And now we see that this part, which was good in the beginning, is still good. It's still orange, and we have no errors on it. But now this region right here is already classified as blue, and that improves our prediction dramatically. We still have some misses here, and obviously a lot of the misses right here in the middle. So we will go on to the third tree and the fourth, and so on and so on. And after 50 iterations, we end up with something like this. And this really captures the structure of the data in this case. It's a very simple case, and I think we could be happy with it, right? And that's really great. The only problem is that we want to use the gradient boosting machines for survival data and not for classification of orange and blue dots with only 2 covariates, right? So we need to make some modifications. First of all, we have to have a loss function that can handle survival data, which specifically I'm talking about censoring. Because in survival data, a lot of times what we have is let's say we have observations of present customers. So they haven't lapsed yet, but I don't know, they can lapse tomorrow, they can lapse next month, they can lapse next year. So I can just ignore them altogether, but then I'm missing out on a lot of data, right? Because if I have someone who's been with me for 3 years, that says something. I know that he hasn't left in 3 years. And that's why we're using censoring, where we will mark this observation as 3+, but we need a loss function that can handle this kind of data. And we need a split criteria that will be able to handle this kind of data, and that's not every split criteria. And just like in any other data that we will have, we will need to do a grid search and find the optimal parameters for the GBM and for the decision trees within this GBM. But if we will do it, we will get a model that doesn't assume any specific relationship between the target and the covariates, and that's what we ultimately want. This flexibility in comparison to Cox model, which is not flexible in that sense. And also, as I said before, you do get some insights into the modeling process, and in this case, we will get insights on which covariates were really useful for the prediction, which are really related to the target, and which are not. We evaluated the performance using simulated data, and we will see it later on. But first, let's discuss those modifications that we need to do in order to use GBM for survival data. So we use the loss function, which is based on Cox partial likelihood, which I assume a lot of you are familiar with. So as you can see, we have we are handling the censoring here using this parameter, and the likelihood itself is very similar to what we are used to seeing in Cox. Only here in Cox we have exponent of beta of x. Whereas here, because we don't want to assume linearity, we have an exponent of some function of x. And this function could pretty much be anything. This function is actually what the GBM is finding. The only thing is, it's a loss function, we want to minimize it, and likelihood, as you all know, we want to maximize, so we add a minus in the beginning, and as I said, we need it differentiable, and that's why we're taking the log of the partial likelihood, and not just the likelihood as is. Okay, great, so we have this set up, and now we are ready to look at some simulation results. So the nice thing about simulations is that you can really build as many data sets as you need, and you can make them as complex as you want or as simple as you want, and you can track down the errors. You can see where you did wrong and then improve them, and that's why we started off with simulations. We simulated over 15 data sets. All of those data sets had 10 potential covariates. Some were binary, some were continuous, and some were categorical, just because that's what we will see in real life. The data sets differ from each other in the number of meaningful covariates, and therefore the number of different behavioral groups. They differ in the time distribution. I sampled the time to event either from an exponential distribution, in which case you get a risk that is constant over time, or in some cases I sampled from a Weibull distribution, in which case you get a risk which is decreasing over time. So in the beginning you have higher chances of lapsing, but if you haven't lapsed in the beginning, it's less likely that you will lapse down the road. And some of the data sets had censored observations and some didn't. And we compared ourselves again against Cox model. And the way we compared ourselves is by looking at the estimation of the survival curve versus the real one. Obviously, the estimation of Cox, the estimation of GBM, and the real one all on the same plot. And when we sample the times from an exponential or a Weibull distribution, then we used parameters which we know because we simulated the data. And in those cases, we could also estimate the parameters using the models and see how far is their estimation from the real values. Okay, so let's look at some results. We're going to start with the simple simulation results. In this very simple case, we have 10 covariates, but only 2 of them are really important for the behavioral groups, and they define 4 different behavioral groups. Those covariates were gender and smoker, so we had female smoker, female non-smoker, male smoker, and male non-smoker. And this is really a setting where a human being may have been able to find those 4 different behavioral groups, because that's just 2 covariates, and they are both binary, so only 4 groups. But still, it would take you a lot of time as a human because you don't know in advance that only those 2 are important. You have to go over all 10 covariates. And some of them have 11 levels or 20 levels. Some of them are continuous. So even though we call this a simple simulation, it's not really that simple. So both GBM and Cox were able to detect that only gender and smoker are important for the modeling process and for the predictions. So that's good and that's nice. And I think that this on its own is very useful and beneficial for actuaries who are working on this field. But when we looked at the estimation of the parameters and curves, we already saw that GBM is doing a much, much better job. So this is just one example. I can't remember which of the data sets it is, but we have 4 groups here. The first 2 groups are the non-smokers, males and females, and the third and fourth are the smokers. They are less common in the population. And we have here lambda is our parameter, and 1 divided by lambda is actually the mean time to lapse in months. So this is the true values, and this is the estimations when we had no censored observation for GBM and for Cox. And these are the estimations when we did have censored observations. And we can see here that GBM outperforms Cox in all settings and for all groups, sometimes not by a lot. Like here we have the real value is 180 and Cox achieves 177.65, so it's not that far, but it's still not as good as GBM. But actually for the smaller groups, Cox misses by a lot. Here, for example, for 174, it predicts 116, so not very good, right? Okay, so let's look at some curves. And this is actually taken from our web platform that we're working on right now. So you can see here, this is the biggest group. We have females that are non-smokers. This is when risk is constant, so it's relatively easier. And you can see that in this case, we have the red curve is the true value, the GBM is in blue, and Cox is in green. And in this case, you can't really see the difference between them because they are all right on the same curve. So all of them did a very good job in this case. But this is the biggest group. If they didn't do a good job in this group, I would be very concerned. But when we move on to a slightly smaller group, we can see that Cox is already somewhat missing the mark, right? And GBM is still right on top of that curve. So this is for males who are a smoker. This is actually the smallest group in the population. And in this case, we are still looking at data without censoring. We move on to yet another curve, and again, we see that GBM is doing a better job. This is when risk is decreasing, and we also introduced censoring, and GBM is still right on top of the true curve, so we were very happy with this. And yet another one, in this case, Cox was over-pessimistic, unlike the previous examples where he was too optimistic. GBM is just doing wonderfully. So we were very happy with those results, and we were ready to move on to complex simulation. So in the complex case, we kept the same 10 covariates, but this time 3 of them were really meaningful, and they defined 20 different behavioral groups. So we had the gender, which has 2 levels, we had the smokers, which had 2 levels, and we also had a covariate called industry, which actually had 11 levels, but only 5 of them were different from each other. So we end up with 20 different behavioral groups. And in this case, both GBM and Cox were able to say gender and smoker and industry are important, but when you drill down to look at which levels of industry are truly important, then Cox did the worst job than GBM. They both, I think, had one covariate which they said that may be important even though it wasn't in practice, and when I checked it out, I saw that it happened to be correlated with the industry covariate, so that explains that. And again, GBM estimation of the parameters and of the curves was much better. I'm not going to show a table of all 20 parameters here because it's kind of a lot, but we do have those plots where we see the deviance of the estimation of the parameter from the real value of the parameter. For Cox, it's the triangles, and for GBM, it's the circles. The size of the group is indicated by the color, and obviously we want all groups, the groups are on the x-axis, and the deviation is the y. And we want everything to be as close to 0, which is the black line here, as possible. And we can see that for GBM, the dots, it's all right there on the horizontal line of 0, so we were very happy with this. For Cox, we can see that it's kind of drifting away, and this is in the case of constant risk, so exponential distribution of the times. And in the case of decreasing risk, variable distribution of the times, we can see that results are not as perfect for GBM as well, but for each one of those groups, GBM is performing better than Cox. There is one estimation which is really off, which is this one. Still better than Cox, which is all the way up here, but definitely missed the mark on this one. So this is something that we would look into, get insights from the model and from the simulations, and try to explore and understand what happened. It's worth mentioning, though, that this is a blue dot, meaning this is one of the smallest groups. And if we would look, obviously I'm going to start with the best groups, the ones that GBM predicted best, but I promise there are going to be some worst groups later on. So in this case, you can see the GBM and the true curve are right on top of each other, and Cox isn't. And I think this example is interesting, especially because if you didn't have GBM, if you would just look at Cox and the real one, you would probably say to yourself, that's not so bad. They're pretty close to each other. If you have had the confidence intervals, it may even be inside the confidence interval, definitely here in the end. But you can achieve much better if you just use the GBM, right? So that's nice. This is another such example where Cox is really not that far away, but it's just not as good as Cox. And you can look right here at which groups those are. So I'm just going to say that we had slightly more female, I think 52% female and 48% male, and about 20% of observations were simulated as smokers. So if you see smoker, it's a smaller group. If you see males, slightly smaller. I don't remember the industry distribution, but they were more or less of the same sizes. So just so you'll know more or less on what we're looking at. This is another example. Again, very good results from GBM, not so good from Cox. And I can go on for a lot of time with the best groups, but I don't think that's that interesting. If we're looking at the worst groups, then we can see that in this case, it's true that GBM is not right on top of the true curve. I'm not even sure if you can see it, but they're not right on top of each other, but they're still very, very close. And again, closer than Cox, which is actually performing pretty good on this group. Another example where Cox misses the mark by a lot, and GBM is only slightly too optimistic, but again, if we were to add the confidence intervals, which we intend to do shortly actually, you would see that it's inside a confidence interval. So even the worst groups are really not that bad. And this is the one that we saw in the beginning that I pointed out that he really missed the parameter, and indeed when he misses the parameter, he also misses the curve. So still better than Cox, which is here, but definitely something that you would be like, I don't think that's good enough. So this is the kind of things we need to work on down the road. obviously. In this case, by the way, I checked, and what happened is that GBM completely missed this subgroup, and so this estimation is the exact curve of a different group to which all of those observations were attributed. So, but that's just because I checked. Okay, so the last thing that we can ask ourselves here today is what else can be done, and the short answer is obviously a lot. So these are just a couple of ideas that we have now. We can think about different loss functions. We use the partial likelihood-based loss function, especially because we wanted to compare ourselves with Cox. But you can think about things that are based on C-index or log rank, which are highly popular in the survival analysis literature. You can think about different algorithms. We use gradient boosting machines, but you can use random forest, which is another method of ensemble learning, but it aggregates a little bit differently, the different decision trees. You can think about neural nets and deep learning, which are very hot topics these days, and everyone likes to say that they're using deep learning, so you can try it here too. You can think about other risk factors. Obviously, this is just lapse risk, but you can definitely make some modification and use it on other risk factors. And of course, you have to look at real data, because simulations are good when you're trying to learn a new problem or learn a new approach and see if things behave as you expect them to. But when you get to real data, you have noise and you have missing values and you have all kinds of errors and typos in the data and strings and integers and all kinds of things that you have to handle. So definitely a lot of work to be done in the context of real data and how to handle it. And with this, I will finish and give the mic back to Effie. So thank you very much for listening.
So thank you, Neta. And right before we start with the Q&As, I'd like to emphasize that you are more than welcome to contact us directly to see how we can help you using machine learning tools in your organization. So I give the control back to Francisco.
Thank you, Effie. Perfect, and thank you, Neta, as well. So we have received a number of questions from the audience, and we can start with that part of the session. The first one is, what are the additional uses of machine learning for an actuary?
I'll take that question. Effie?
Excuse me, do you hear the question?
I heard the question. Do you hear me answering?
Yeah, the question is, what are the additional uses of machine learning for an actuary?
David, are you there?
Neta will answer.
Okay, Neta, go ahead, please.
And sorry, I meant I will answer the questions that are in the chat box. David, go ahead, sorry.
Okay. So additional use for machine learning is on various levels. We showed here, and some of them Neta alluded to in her presentation. Do you hear me all right?
Sure.
Yes, we do.
Okay. So in addition to improving the solvency model and the prediction of the expected cash flows of the insurance business, the machine learning also can be used for basic business decisions in the earlier stages as to what business sections and what target market you're going to want to address, which you're going to find out by doing the machine learning analysis. You can find out which are the less dangerous and which are the more dangerous sectors. And based on that, you should be able to allocate your capital better. So that's one use of the machine learning. And another one, which Neta alluded to towards the end, is that you can improve your solvency model in terms of setting the confidence around your parameter setting by using a machine learning algorithm.
Great, thank you. We have another question. The tool that you're using, what is the flexibility of this tool, and do you offer open source code? David, Neta, will you be taking that one?
So we do not offer any open source code at this stage. What we offer at this stage, because we are a startup and we were in the beginning, we do have a lot of flexibility in the sense that if you have a specific problem that you're interested in or a specific domain where you want to introduce machine learning, then we are open for suggestion, we are open for discussion. And if there is enough data and there is labels and everything that we need in order to build a model, then we're definitely interested in hearing about it.
Thank you. One more question is, what are the benefits of using machine learning in the context of Solvency II?
Yeah, one additional benefit that I came to this whole enterprise with the actuarial view, with not much background in machine learning at all, just curiosity. But one thing I understand is certainly going to be beneficial is that the whole process of setting parameters is going to, on the one hand, be streamlined. It's going to be incorporated into the solvency process, and as such will be more organized. It will be more easily updated, and it will be able to self-train and use the accumulating data that we're just at the beginning of accumulating it. And as time goes on, we'll have more and more certainty around the results that this algorithm is going to produce.
Thank you. How often do the models need to be updated, and by whom?
So I think this is really up to the customer, up to the insurer. I don't know what is currently used, but theoretically they can be updated every night. In practice, you don't need to update them every night. You won't see big differences, and it would be just time-consuming. And obviously, the insurer doesn't want to wake up every morning and to find that he has a different capital requirement, right? So this is really a business question in the sense that whatever the insurance wants and whatever the data requires, we can do. It's not a problem to update it. It doesn't overflow the system or anything. It can run overnight, and you just wake up and you have the new predictions.
Thank you. How do you decide which algorithm to use?
So obviously, as I said in the last slide, there are a lot of algorithms, and you can pretty much start with whatever you want. There are a couple of guidelines, like a lot of people like to use neural nets or deep learning because it is the buzzword now, but a lot of times you don't need them. You don't need all of this complexity, and you don't need the additional overhead of trying to understand what's going on there, especially if you don't have a lot of explanatory variables. So neural nets are more appropriate when you do things like image segmentation or pattern recognition, where you have all those pixels and those are all explanatory covariates, and you have hundreds or thousands of explanatory covariates. But for simple data, a lot of time decision trees or ensemble methods are efficient, and you also get the benefits of actually understanding what's going on in the modeling process. As for should it be a GBM or a AdaBoost or a random forest, there isn't one good answer. We will probably try random forest as well down the road. We started with GBM because empirically, from my experience, it tends to work well on this kind of problems, and it had a nice implementation in R, so we decided to start with that.
All right, thank you. We've got a few more. Is it possible to understand which variables affect the outcome more, and some quantitative factor by how much?
Yeah, so I briefly mentioned it. You do get, for GBM, for example, there is something called feature importance, where you get exactly that. You get each feature, each explanatory covariate, what was his contribution to prediction, how useful it was in a scale of 1 to 100, I think, in R, such that the summation of all covariates is 100. So you know in percentage how important this covariate was. And then, you know, you can say, oh, that makes sense, or that doesn't make sense, or if there is something that is consistently rated as low importance, you may leave it out of the model. If you have something that is consistently found important, maybe you can add more data that is related to it, or maybe you can collect more data about it from customers and so on.
Thank you. What distinguishes a weak learner as a weak one, and what are the other categories?
Yeah, so when we say weak learners, it's just a term to clarify that each decision in this model, each decision tree on its own would probably have a lower accuracy or lower power than the entire ensemble combined. So it's weak in that sense, but it's not necessarily weak. I mean, there are data sets where just one decision tree can do a great job and you can get great predictions. So it's not weak in the sense that it doesn't work. It's weak in the sense that its predictions are probably less accurate than the predictions of the final ensemble model will be. And theoretically, it could be a lot of different models. It doesn't have to be a decision tree. In practice, for GBM and for random forest, I do not remember ever seeing anything other than decision trees.
Thank you. Is the loss function used to split a node into daughter nodes?
Yeah, so in this case, we really used, it wasn't exactly the loss function, but it was some function that is based on the loss function in the sense that we said that the best split is the one that causes the most constant decrease in loss function or something of that sort. I don't remember the exact function, but it was based on the loss function. But I know for classification problems where let's say you want to decide if a person is going to churn or not, or you want to decide if you should offer a certain product to a certain person, it's a yes/no question. Then splitting criteria very oftenly are some measurements of the homogeneity inside each resulting node and how different are the nodes from each other. Things of purity. We want the nodes to be as pure as possible and to be as far away from the other nodes as possible. So we use those kind of split criteria.
And finally, what kind of data can best be used in machine learning for prediction of mortality rate?
David, I think you want to take this?
I'll take that. I mean, mortality is just one risk factor, and I think the power of machine learning is going to be able to use vast experience, but also well-organized and classification of that experience. So to just know that people died at a certain age, the more data you have doesn't necessarily lend itself to the machine learning being a powerful tool. Where the power of the machine learning is going to be added is you're able to classify as to who the mortality stems from, like his health data that you may follow over time, or his lifestyle situation, which sales channels you had, what the family situation may be, in which year things occurred in order to follow this data over time, etc. So it's really to make sure that the exposures and the claim side has as much classification and parameterization along with it, so that the machine learning algorithms is able to then tell you which of these parameters had a significant effect and should be considered and which of them are less, and also quantify them.
Well, thank you, everyone. This actually brings to an end our Q&A. We hope you have enjoyed this webinar from the Actuary and RemitRix, and Before we go, I would like to thank again to our speakers, Effie, David, and Nita. We'd also like to thank RemitRix for sponsoring it. Finally, before we leave, I would like to remind you to complete the short survey that follows the webinar. So with that, enjoy the rest of your day, and I look forward to your participation in our next webinar from the Actuary. Goodbye. Thank you.